Students, I hope that you are good, well, and fine. So, in today's session, we will be covering about adjoint of a matrix. Okay, and then if time permits, then we will be seeing how we evaluate inverse of a matrix using adjoint. Okay, we already know how to find an inverse, the inverse, using what? Using elementary row operations. Okay. Now, first of all, in today's session, we will be covering about adjoints. Okay. So, adjoint of a matrix, and then we will be seeing some remarks and some theorems, and then singular and non-singular matrices, and then we will be covering, if time permits, the remaining subtopics. Okay. So, adjoint of a matrix is just nothing, but it is defined as a transpose. So, what do we mean by transpose? Let me just recall you quickly. So, transpose means changing row entries to column entries and column entries to row entries. Suppose you have 2 cross 2 matrix like this. Okay, then its transpose denoted by AT or A prime, A dash will be what? This row 1 will be changed into column 1, means A11, A12, and this row 2 will change to column 2, A2, A22. That's it, your A transpose. Okay, I hope that now you recall or you remember it. Now, and your adjoint of a matrix A matrix is this of order n, and it is defined as the transpose of a matrix. What matrix? Adjoint of matrix A is a transpose of what matrix? This matrix, and this is what your cofactor entries. So, if A is your this matrix of 3 cross 3 order, then first of all you have to evaluate your what? Adjoint. Sorry, you have to evaluate your cofactors. After evaluating your cofactors, suppose A11, A12, A13, A21, A22, A23, A31, A32, A33. Then put these entries in a 3 cross 3 matrix. Okay, and if you transpose it, if you transpose this matrix, you will get your adjoint A denoted by ADJ bracket A, adjoint A. Okay, so your adjoint will be this thing. Okay, so transpose of this matrix. These capital AIs are the cofactors. Okay, simple. Or in another term, in another form, adjoint A will be A11, A12, A13, A21, 22, 23, 31, 32, 33. Okay, clear? Okay, now let us see some example. So we have to find the adjoint of A. So in order to find adjoint of A, let me find matrix B, in which in this I have to find A cofactors A11, A12, A21, A22. Okay, so for A11, it will be M11, A21, sorry, A12 will be minus 12, A21 will be minus 21, and A22 will be M22. Now, A11, M11 means eliminate first row, first column. You will left with this. 1, 2 means eliminate first row, second column. Minus 1. Okay, first row, second column. Now, eliminate second row, first column. So 3, it will be minus 3. Now, eliminate second row, second column. So 2. Okay, so this B matrix, the cofactor matrix will be 4, minus 1, minus 3, and 2. Yes, now transpose it. So B transpose will be, this row will turn into column, this row turn into column. So this will be your adjoint of A. Simple. So 4 minus 3 minus 1, 2. So this will be your adjoint of A. Okay, clear? Okay, now what? For a square matrix of order 2 given by this, the adjoint of A can also be obtained by interchanging A11 and A22 by changing signs of A12 and 21. What happened? As you can see that in previous, what just happened, that these position interchange. 4 is now in this position, at this position, and 2 is now at this position, as you can see. And what happened? And you just put minus sign extra over here. So as you can see, so in 2 cross 2 matrix, in general, what is happening? A11, A12, A21, A22. This, if this is your matrix X, then adjoint of X will be directly evaluated by what? Doing what? Interchange their positions of main diagonal entries A22, A11, and just give extra minus sign to the other diagonal entry. You will have your direct, you do not need to evaluate any extra like this. Okay, you do not have to worry about extra calculations. Okay, so in general, this will be your approach in case of 2 cross 2. Okay, remember this point, in case of 2 cross 2. Okay, so adjoint of A will be now A22, A11. The main diagonal entries will be interchanged, and the other diagonal entries will be having extra minus sign. Okay, now if someone asks what will be your adjoint of this matrix 2, 6, 8, 9, you can directly say, quite simple, directly say this will be your 9, 2, minus 8, minus, like this. Yes, how quickly you just evaluated it. Okay, what about this 0, 1, 1, 1? What about this? So this will be interchange, now minus extra minus sign. Okay, what about CD? So this will be minus C minus D. Very easy to find adjoint now in case of 2 cross 2 matrix. Just interchange the main diagonal entries, just interchange and put minus extra minus sign to the remaining entries. Okay, clear? Okay, I hope that this remark is very clear to you. Now let us move to next theorem. We are not going to prove any theorem, okay, as you will get confused here. The main thing is to get what theorem says and how we will apply theorem statement. Okay, how we will apply the theorem statement in questions. Okay, how to solve. Okay, our main objective will be how to solve. Now, if A is any square matrix, so first of all, A must be any square matrix with order n. Okay, now your A multiply adjoint of A will be same as adjoint of A multiply with A determinant of A multiply with identity matrix. Okay, so we are not going to the proof, but we will provide you some verifications, okay, so that you satisfy your curiosity that indeed this theorem is true. Obviously, that's why it is theorem. So take example of this 2 cross 2 matrix A11, A21, A22. Okay, now adjoint of A will be what? As you know, directly you can come A22 minus A12 minus A21, A11. Simple. Now just multiply. Now A adjoint of A will be what? Just multiplying. You know, this row will be multiplied with this. What you will have, as you can see, or in other forms, what you can write it as, you can directly say A11, A12, A21, A22. These are what? Capital A's are cofactors. So capital Aij are cofactors. cofactors. So this will be what is happening, a11 plus a12 a21. Okay, as you can see, this going to multiply with this. Okay, so far so good. Sorry, the transpose, you all know the transpose. So a21, sorry, a21 a12, what, let me once again give you. So adjoint of a is what, just nothing but the transpose of a11 a12 a21 a22. Okay, so transpose will be what, a11 a12 a21 a22. Okay, clear? Please do not forget to apply this transpose. Okay, so this will be this. Now a11 a11 a12 capital A12. Okay, clear? A12 A21. Clear? Okay, so how we got this? By just the definition. We use definition thing. Okay, definition. Now what? Now this entry will be what? So let me make some space. Okay, so you will be having 2 cross 2 matrix. So first entry will be a11 capital A11 plus a12 capital A12. Now this will be a11 a21 plus a12 a12 and a12 a22. Okay, what about this? a21 a21 a11 plus a22 a12. Clear? Now what? Now a21 plus a22 a22. Now one thing, if you remember, what what, that a11 multiply with a11 plus a12 multiply with a12 will give you what? Determinant of 2 cross 2 matrix. Yes, so this will be determinant of this. Yes, 2 cross 2 matrix. Okay, the same thing will happen if you multiply a21 plus a22 a22. Yes, you will get the same determinant. Okay, so I can rewrite this as, we already know this will be your determinant of it. This will also be your determinant of it. What about these entries? So let us evaluate these. So we are given a11 a21. Yes, I'm talking about this entry, a11 a21, and yes, a12 a22, a11 a21 a12 a22, sorry, a12 a22. Yes, this is what written over here. Okay, now evaluate it. You all know a21 means a21 will be minus, so a21 will be minus of m21, and m21 will be what, eliminate second row and first column, you will have minus 1. Yes, minus 1 2, so minus 1 2 plus a12 a22 will be m22 means eliminate your second row second columns, you will get a11. So this will be a11. Now what you will get? Minus of a11 a12 plus of a11 a12. This means 0. And you also remembered from theory class a remark point that this, if such a sort of thing is happening, means that elements of a row, so this is first row elements, are multiplying with any other row cofactor or any other column cofactor. As you can see, these are the cofactors of the second row. Yes, so they are multiplying with these, so you all know their sum must be 0. Their sum must be 0, as you also saw here. Yes, so try to memorize that point or prefer the previous session in which we discussed this remark. Whenever you have row entries, any row entries, so these are first row entries, multiply with, so any row entries multiplying with any other, we are talking about any other row cofactors. So these cofactors are from what row? Second row. Yes. So my first row elements are multiplying with second row cofactors. Whenever this happens, you will be always having the sum equal to 0. Okay, the sum equal to 0. Clear? Okay. So this will be 0. On the same pattern or using the same point or the remark, this will also be 0. Okay. Now what you will do? Now you can take a common. So taking a common, this will be I. This will be, sorry, not I, this will be 1, this will be 1, and you took a common, not a, the determinant a common. So, okay, this is what your identity matrix of order 2. So this will be what? I2. Okay, this will be what? I2. I2 means identity matrix of order 2. As you just verified using 2 cross 2 matrix, that adjoint A multiply with adjoint of A is same as adjoint of A multiply with A. You will always having determinant of A. Just determinant of A, you can say. Okay. Simple. Or you can just eliminate I. Okay. Clear? Simple. Not you cannot eliminate, sorry. You will always have determinant of A multiply with I. Okay, sorry for that. You must have to write in this form A, determinant A multiply with I matrix. So you will always have this outcome or this result. Clear? So we are not going to the proof. We just give you for 2 cross 2. Okay. And the same pattern you can also do for 3 cross 3. Okay. But here we are talking about any number n, not any natural number n. Okay. So 1, 2, 3, 4, 5, anything. Okay. So I hope that it is clear. Let us move to next. Now, singular matrix. What do we mean by singular matrix? So singular matrix means matrix having determinant 0. If a matrix is its determinant is 0, then it is a singular matrix. So for example, A, B, 0, 0. Is this a singular matrix? Yes. If you evaluate its determinant equal to 0, so singular matrix. This is a singular matrix. This matrix is also a singular. 1, 1, 2, 2. This matrix is also a singular. Okay. Clear? So I hope that it is clear. So when do we say matrix is singular? Means whenever you have determinant equal to be 0. Okay, what if determinant is not 0? Suppose A 1, 1, 1, 1. Here determinant is not 0. Then we will say it is a non-singular. Non-singular. So you just have to remember this, and just you have to remember this singular. What do we mean by singular? And opposite of this singular will be your what? Non-singular. Okay. Okay. So if you try to memorize both, then you will get confused that when this happened, what we say, and when this happened, what we say. So just you have to remember only one, which is this. Whenever you have determinant equal to 0, then you will call it as that matrix as a singular matrix, and opposite of that means non-singular. Non-singular means non-singular. So non means not 0. Okay, you can try to find some pattern so that you can easily memorize them. Okay, so non means not equal. Non-singular, not equal to 0. Okay, as we saw just example. So another example will be like this. Okay, so not 0. Clear? So quite simple. Okay. Now, if A and B are non-singular matrices of same order, then AB and BA are also non-singular matrix of same order. So this is quite interesting thing. What it says, if determinant of A is non-zero, if determinant of B is non-zero, okay, then determinant of AB and BA both are going to be non-zero. Okay, clear? So we are not going to the in the proof. Okay, clear? So this will happen. You will see how we are saying that this will happen. You will see a property of determinant, that a determinant of AB is same as determinant of a determinant of. So using this, you will see that as it is non-zero, this is non-zero, then total product will also be non-zero. Okay, clear? Okay. So I hope that it is clear. Now let us move to next problem. Okay, so more determinant properties. So the determinant of a product of matrices is equal to the product of respective determinants. What it says, that as we just discussed, that if you have two matrices AB, if you product it and find the determinant, it will be the same output as if you find the determinant of A, determinant of B, and then product. Okay, this. Okay, so let me give you some examples. Suppose A is 1 2 1 3, okay, and this matrix, and B is what matrix? Say 1 6 1 1. Okay, now determinant of A will be what? As you can see, 3 minus 2 1. This will be determinant of B will be minus 5. As you can see, 1 minus 6 minus 5. Okay, clear? Now AB, product of AB will be what? As you can see, 1 2 1 3, 1 6 1 1. Okay, 1 6 1 1. The product will be 1 multiply 1. So this row going to multiply with this column. So 1 1 plus 2, this will be 3. Now 6 plus 2 will be 8. Now 1 plus 3 will be 4. Now 6 plus 3 will be 9. Okay, and now the determinant for AB will be, as you can see, it will be what? 27 minus 32. What? It will be what? Minus of 5. As you can see, minus of 5. Now minus of 5 is what? As you can see, 1 multiply minus 5. Yes, and 1 is what? Determinant A, and minus 5 is what? Determinant B. Okay, so please satisfy, make comfortable yourself through this example, that indeed product of AB determinant is same as product of determinant A, determinant B. Okay, easy. Okay, so please do remember this. Let us move to next. Now one more interesting property of adjoint. Okay, so adjoint of A, okay, adjoint of A, determinant, adjoint of A whole determinant is same as saying determinant of n minus 1. N is what? Order of the matrix A. Okay, let us also verify that. Suppose you are having 2 cross 2 matrix. What? 2 cross 2 matrix. Suppose A11, A12, A21, A22. Okay, now adjoint of A, you all know adjoint of A. Directly you can evaluate your adjoint of A. So interchange the main diagonal entries and give extra minus sign to remaining entries. Okay, this will be your adjoint. Now it's a determinant. Now find the determinant for this adjoint. So determinant for this will be determinant for this. Okay, determinant will be A11, A22 minus A12, A21. As you can see, this is what? Your determinant. This is what? As you can see, determinant of A. Yes, this is what your determinant of A. And this is just nothing but determinant A 2 minus 1. This is what happening. Yes. Okay, I hope that it is clear. So this is for 2 cross 2. The same way you can do for 3 cross 3. Okay, but it is true in general, having an order, a square matrix, a square matrix having an order will follow this thing, this pattern. Okay, so let me once again recall you so far what we came across. Determinant of A can be through what, any row. Okay, so pick any row. Suppose in 3 cross 3 matrix, we are talking about 3 cross 3 as well as 2 cross 3. So picking row 1 in 2 cross 2 matrix, what you will have for 2 cross 2. Okay, this will be A11 row 1. I am choosing row 1, A11 plus A12, A12. Okay, now this will be same as A21 plus A21, A21. Okay, in case of 3 cross 3, this will be A13, A13. Okay, and this will be A23, A23. And the determinant, this is just what? Determinant. Okay, and A23 plus, sorry, A21, sorry, A31, A32, A32, A33. You can do along with what? Your column also. For example, choosing column 1. So column 1 is 1, 1, A11, A21, A21, A31, A31, like this also. Okay, simple. Now, in case of 2 cross 2 and 3 cross 3, you have one interesting property that whenever a row entries, suppose in 2 cross 2 matrix A11, A12. Okay, in 2 cross 2 matrix A11, A12, 2, 1, 2, 1. Okay, A11, A12, 2, 1, 2, 2. Okay, if a row entries are multiplying with another, okay, other row cofactors. For example, cofactors for second row will be A21, A22, like this. So A21, A22. Then this sum will always be 0. Then this sum will always be 0. Okay, please remember this. Okay, clear? Then this sum will always be 0. Okay, what about in 3 cross 3? Okay, let us see also. So A11, A12, A13, A21, A22, A23, A31, A32, A33. Now, if you do what? Say A11 and multiplying with second row cofactors, A12, A22, A13, okay, A23, like this. Now find, so we will see that it is indeed 0. Okay, so A21 will be what? Let me quickly find out. A21, A22, A23. Okay, so A21 minus, it will be plus, it will be minus. As you can see, 2 plus 1 will be 3, 4 and 5. Okay, so it will be M21, M22, M23. Okay, M21, eliminate second row and first column. So this will be A33. So A33, A12 minus A32, A13. Okay, using extra minus this, you will have this. Okay, so far so good. Now M22, eliminate second row, second column, A33, A11, A33, A11. Eliminate second row, second column. Okay, A31, A31, A13. Okay, so far so good. Now 2, 3, eliminate second row, third column. Okay, so A11, A32 minus A12, A31. Because of this minus sign, you will have this. Okay, now what is happening? Now A11 is going to multiply with this A21. So you will have minus A33 A12 A11 plus A11 A32 A13. Okay, simple. Now plus this A12 multiply with A33 A11 minus A12 A31 A13. Okay, now minus A1 or sorry plus A13. Okay, A13 A11 A32. This will be of minus A13 A11 this. Okay, or plus A13 A12 A31. Now try to observe what. So 131132 131132, this will be cancelled. Okay, clear? Now what? 1312 1312 31, as you can see, cancel. 123311 123311, this will be cancelled, as you can see, 0. Okay, so please also remember this. If such a sort of thing is happening, then you can directly say it is equal to 0. Okay, if entries of a row are going to multiply with another row cofactors like this, then you will say directly that their sum must be 0. Okay, clear? Okay, and what you just also find out that adjoint. Okay, I hope that it is clear. Okay, so adjoint of a determinant will always be determinant of a n minus 1. Okay, clear? Okay, so you saw these, as you can see. So that's it for now. I hope that you understood properties, different properties. You saw different types of examples. You saw different types of properties. Please do practice more. We will be back with more examples and more questions based on the basis of these properties and theory we have covered. So thank you all. We will be back soon. Again, thank you.